Hello, everyone. My name is Jiaji Hu. I'm from Mangan Inc. We are an engineering consulting firm located in Long Beach, California. Today, I'm with my colleague Aditya Kali to present an ETAP case study titled, Should Motor Starting be Evaluated when Mitigating Arc Flash? So here is the agenda for today's presentation. We're gonna present you a real-life project, introduce the project background, the ETAP studies we have done, the challenges we're facing when giving arc flash mitigation recommendations or proposed solutions, and finally, we're gonna do a brief system demonstration on ETAP 2024. First, I wanna talk a little bit about some key considerations we have for arc flash mitigation recommendations. Here at Mangan, over the years, we have done a large number of arc flash projects for different clients. We have gained the experience that when talking about arc flash mitigation recommendations, it's not as easy as just list all the available solutions on the market and throw the list to the clients. We should be more responsible to find the most suitable one for the clients. So here I summarized some key considerations. First is that the consideration must be effective. It must be effective enough to bring down the system high IE down to a designed level for all the different system configurations. The second one is practical. The recommendation has to be feasible and easy to realize. It should comply with different aspects, such as the existing equipment condition, the client safety regulation, or even the client budget. For example, installing a differential relay on a bus can probably bring down your high IE to a very low level. But differential relay has more consideration, like city wiring, your distance from the city to your relay, even nuisance tripping. So differential relay may not always be the best option to recommend. The third one is about balance. Any recommendation we are giving, we should not ruin the condition of the system, such as load flow stability, your protective coordination, or even your motor starting, as we're gonna discuss later. Even if sometimes we need to compromise some aspects, it should be fully considered and evaluated. The fourth one is about creativity. It's really talking about, as an ETAP user, we should know that ETAP is a very powerful software. Lots of the arc flash mitigation techniques on the market, they can actually be smartly integrated into the ETAP model. So when we run the study, it can give us more realistic arc flash study results. So here we happen to recently done a project that is a perfect example of mixing all these considerations. So here's the project background. A refinery client has a 2.4 kV double-ended substation, which was built a long time ago with old type switchgear. The switchgear has a very low bracing rating. So historically, there are two line reactors installed at the 12 to 2.4 kV transformer secondary side to limit the short circuit current into the substation. The transformers and the substation buses has enough capacity for future expansion. So now the client wants to add an 800 horsepower motor to the substation. A series of feasibility studies must be performed before they do the addition. The primary concern for this addition would be the motor starting analysis and any potential arc flash impact comes with the system change. So here we can see the system has bus A and bus B. They have a tiebreaker to tie the bus, and there are two line reactors, A and B, connected. So the first step is to do a motor starting analysis. We developed 4 configurations to run a static motor starting analysis. Those configuration would include the first one, the normal configuration. We have all the tie breakers open and all the main breakers closed. This is the ideal configuration that has the best motor starting profile. Then we also have here the substation parallel configuration, which is the two main breakers are closed and also the tie breaker is closed. This is actually a temporary stage that the client doing switching sequence. But per their standard, this configuration should also be considered for the arc flash and the motor starting. And also, of course, we have the substation single end configuration, which is 2 and 3 here. When you have the tiebreaker closed, one of the main breaker closed, and the other one open. By engineering experience, we know that probably the single-ended substation give us the worst motor starting peak profile. So that's why we have a no reactor and the reactor case to compare how much voltage drop is actually brought in by the reactors. So when we run the study, we can see from the curve here that our scenario number 3 with reactor and the system single-ended has the worst case that your voltage drop is over 17% and your motor terminal voltage when starting is barely about 60%. And you have a significant bigger motor acceleration time. So under this scenario, probably our sensitive equipment in the system can drop out. So it's considered a failed motor starting results. So the decision here is to remove the 2 reactors and replace it with a bus duct to facilitate a healthy motor starting. So with a system modification like this, we know that your arc flash assessment needs to be updated for any potential arc flash result change. We run the arc flash, so I put a table here to summarize the results. You can see that for the substation 2 bus A and bus B, and the 2 main breakers, they all got a very high incident energy. This is first due to a very high fault current because removal of the line current. The second is that the substation relays are old electromechanical relays, and only the time over current function is enabled at this stage for better coordination with downstream. So with time over current, the 4 locations all got a very long FCT to clear the fault. So they got a high incident energy here. So here we're providing our solutions, and here are the main mitigation challenges we have. The first one is that with the line reactors being removed, we still want the short circuit to maintain the lower level as before to protect the old switchgear equipment. The second one is that we should allow successful downstream motor starting under all system configurations. The third one is that we want to reduce the IE on the substation and its main breaker line side to below 8 calorie under all system configuration per client standard. The fourth one we need to consider is that this is an outdated switchgear with very old equipment. And with a limited budget, it's not very easy to just recommend like more common relay upgrade options like differential relay installation or switch to a microprocessor relay with arc flash maintenance mode. So here we really need a more customized solution to be offered to the client. So from here, I'm gonna pass to my colleague Aditya to present you our solution for this condition.
Thank you, Jaji. Hello, I'm Aditya, and I'll be presenting the customized solution we propose to the client. Our focus will be on addressing the key system challenges, followed by a demo in ETAP 2024 to showcase how we can model the solution and generate accurate results. So, the proposed solution? Installing a fault current limiter. Given the challenges, our proposed solution directly addresses the 2 critical issues. 1. The existing reactor causes a significant voltage drop, which is further exacerbated when starting large motors. And two, removing the reactor reduces this voltage drop but significantly increases the short circuit current. This scenario creates an opportunity for a solution like adding the fault current limiter FCL, also known as a triggered current limiter TCL. Before we jump into the ETAP demo, let's take a moment to understand the FCL. The FCL is an electronically triggered current limiter that operates by sensing and quickly interrupting fault currents before they can cause damage. Here are a few key components of the FCL: the current transformer inputs that sense the current levels, the copper bus bar which carries the normal operational current. Positioned above the bus bar is a fusible element ready to respond in an event of a fault. The entire operation is managed by the firing logic, which controls the pyrotechnic actions of the limiter, which requires a external power source. How does the FCL operate? Let's break it down. Under normal conditions, the copper bus bar safely carries the load current. In the event of a fault, explosive charges located under the bus bar are triggered by the firing logic. This causes the bus bar to be physically severed. As the conductor is being cut, arcs form in the resulting gaps. The short circuit is thus diverted to the fusible element, which rapidly melts and clears the fault. The entire process occurs within a quarter of a cycle, meaning the fault is cleared before the first peak of the fault current, drastically limiting the damage. Now, I think is a good time to jump into the ETAP 2024 demo. So, here we have the ETAP 2024 demonstration for our project. We have a dummy model set up for this presentation. Let's look at it. We have an upstream 12 kV substation in a double bus, double breaker configuration, which feeds two transformers T1, T2, on the secondaries of which we have our reactors A and B, which are then feeding our substation. The substation is labeled bus A and bus B. We have the substation in a main tie main configuration. This 800 horsepower motor is the new load that is to be added on bus B. Before running any system studies, we have set up all possible configurations for the particular sub. We have a normal configuration where the substation is double-ended, a paralleled configuration during the switching, and a single-ended substation configuration where the entirety of bus A and bus B is fed through one transformer. So let's look at the issue of why the reactors, why we can't start the motor with the reactors in circuit. Let's look at the load flow study. I'm going to start the study with a normal configuration. Here we have the motor bus voltage at 89%. Keep in mind this voltage drop is because of the losses and drop across the reactor. At 89% starting voltage, the motor can still be successfully started. In a parallel configuration, we have the same case. However, in the single-ended scenario, which is the worst case for us, the motor initial voltage drops drastically to 82.5 volts. In our project that we did, this number was close to 81%. The numbers are manipulated here for the sake of the presentation. So now, given our initial starting voltage of 82%, starting a large horsepower motor in this configuration is almost impossible. The reason we say that is during the motor acceleration, this voltage is going to further drop an additional 15 to 16%, which takes it close to the contactor's drop-off voltage. So during the starting of this motor, there is a chance that these contactors might just open up and we lose the loads for no reason. This led to a conclusion that we cannot start the motor with the reactors in place. So an obvious solution to this one, we just take the reactors out. That takes us to Model 2.0, where we have the exact same substation, but the reactors are removed. The buses are renamed to Bus A and Bus B, no reactor. Let's take a look at the motor starting here. The load flow study. So we can look at the voltage in a normal configuration. We have the motor starting voltage at 97%, which is very healthy. For the paralleled, is the same. And let's take a look at the worst case single-ended scenario. We have a motor bus starting voltage of 95. That is a tremendous improvement over 82% voltage. Now we have about 95% voltage. So the motor can be successfully started even with a 15% voltage drop during acceleration. The contactors are safe and we would not have any nuisance trip. So we can successfully start the motor based on the voltage evaluation itself. However, removing the reactors, we have exposed the substation to high short circuit current. How high? Let's take a look at the numbers. For the short circuit study, to save time, I have set up some scenarios. And I'm just going to use the ETAP study wizard to just run through all the possible all the set scenarios. The study is running through the normal and the paralleled configuration. So let's take a look at the results. Here we see the results for the substation model 1.0, model 2.0. We have the short circuit increasing significantly from 23,000 all the way to 38,000. But I still don't see any flags here. My system is still healthy. Everything looks fine. We can start the motor as well. So what's the issue? When I look at the asymmetrical fault current, this is where a flag pops up. We have the short circuit approaching marginal alert because my system is rated for a 58 kiloamp short circuit. The system fault current is about 57. This is too close to be comfortable and needs to be remediated. Now we also know that increased short circuit is going to increase our arc flash results as well. So let's take a look at the arc flash results. I have the study set up. The analyzer will show us the results here. Let's disable the fault current. We'll look at it later. So what do we have here? So if we take a look, the results don't look good. Uh, in both the scenarios, we have high arc flash incident energy. And we can see with the bolted fault being 19,000, it jumps up to 32,000 in the case for when the reactor was removed. The reason for this high incident arc flash energy is the upstream devices that we have, they are electromechanical type and they do not have advanced arc flash mitigating features, and nor do we have a 50 element enabled on these. So it takes a lot of time for these relays to acknowledge and clear the fault. Thus, we have to rely on the 2 second rule, so the fault gets cleared in 120 cycles. So we can see the energy is worsened when we take the reactor out. Now, coming to our solution, model 3.0 has the fault current limiter modeled. How do we model the fault current limiter? The copper bus bar that carries the normal load current is modeled in form of a contactor. This contactor is controlled through this overcurrent relay. The overcurrent relay receives a signal from the CT that's already mounted on the FCL. How does the fault current limiter work on the model? It all lies into the pickup that we set on the overcurrent relay. So in the market, FCL are available in various sizes. So the sizes, the way these are specced out is we have something called as a trigger current limit. They are available in various voltages and multiple trigger currents. For our case, the trigger current that we rely on is 10,000 amps. So that is how that is how we set the overcurrent relay. The overcurrent relay needs to be we can use any generic overcurrent relay here. I've used a Schweitzer in its place. So what does a trigger current limit mean? For the FCL, any time the fault if the fault current exceeds that trigger level, it basically triggers the overcurrent element, which in turns opens up the contactor. Once the contactors open up, we know the short circuit flows through the fuse, and the fuse rapidly melts and clears the fault. It's important to size the fault current limiter carefully, keeping into mind important things such as your load current and any inrush currents that we may have. For our circuit, 10,000 was a safer limit. However, if any of my inrush currents exceeded that 10,000 amps, I would have to rely on the next available size for the fault current limiter. So let's look at the fault current limiter in action. We can run the arc flash study. There we go. That was pretty quick. Let's look at the analyzer results that we have. So let me add in the FCL. Boom, right off the bat, we see it. The results are considerably good. The reason being, so we can see the fault current remains the same. So it's the exact same as the case was with the no reactors. But we have a very fast acting device here that acts up in 0.6 of a cycle, uh, which leads to very low incident energy. Uh, so that's so we look at the arc flash results. Another thing to note here is the placement of these fault current limiters. Because these are placed on the secondary of the transformers, we get something that is desired by by many arc flash mitigation techniques, is the low incident energy on the line side of the main breakers. So right now, the whole substation, including the line side of the main breakers, has low incident energy thanks to the fault current limiter. And we can take a look at the quick look at the load flow study for the worst case scenario, which is the single-ended. And we can see we have a healthy starting voltage of 95%. The motor can be safely started. So even if you have a 15% voltage drop during acceleration, the contactor should be good, and we would not have any nuisance tripping during acceleration. So we can have a very successful motor start as well. That's the end of the ETAP demonstration. Let's summarize our study finding and conclude the presentation. Back to the presentation, let's summarize the ETAP study findings. We looked at the load flow study where we saw the motor cannot be successfully started with the reactors in circuit. This was primarily due to the low initial motor bus voltage. Removing the reactor does boost the initial voltage up to a comfortable level where the motor can be started without dropping off any other loads. Then we looked at the short circuit study where the system marginally fails because of the high short circuit duty when the reactors are removed. Adding the fault current limiter device protects the system from this high short circuit current. We then looked at the arc flash study. For the arc flash study, the incident energy was above 40 calories per centimeter square for scenarios with and without the reactor. However, adding the FCL has not only limited the short circuit current, but it's also isolating the fault fast enough to yield a very low incident energy result, which is less than 2 calories per centimeter square. Let's also look at, I have a brief snapshot of the motor starting study that we did. What this shows is the voltage drop during acceleration. So in the in the single-ended scenario with the FCS in circuit, we see the initial voltage is slightly above 95% voltage. And at 0.5 seconds, we start the motor where we have a voltage drop during motor acceleration. This takes the motor bus voltage up to around 88 to 89% of the voltage. This is the drop during the motor starting. This voltage drop does not affect any other associated loads. There are no other risks to the motor starting. So we can conclude with adding the FCL, having no reactors in circuit, we are able to start the motor successfully. In conclusion, I want to emphasize on saying that the arc flash mitigation recommendations have to be customized for each system, and this is it's important also to evaluate the interplay that we saw here between motor starting and arc flash analysis. The solution that we present here balances the motor performance along with the arc flash mitigation. So key takeaway here: ensure safe motor operation, safe motor starting, along with arc flash protection through thoughtful system design. Thank you very much. We are open for any questions.